University. It's my great honor to welcome you to join EcoMat webinar today. Today's topic was green fuels from materials around you. First, I'd like to invite Ms. Jiahui Diao to introduce EcoMat journal. So please.
Thanks, Professor Zhang. Good evening, also good morning and good afternoon, everyone. Welcome to our EcoMat webinar series. My name is Stacy Diao. I am the Journal Publishing Manager of EcoMat from Wiley, China. First of all, please allow me to give a quick introduction about our journal. EcoMat is a flagship journal published by Wiley in collaboration with the Hong Kong Polytechnic University. It is a gold OA journal, and we aim to publish on a wide variety of topics from different disciplines that share a focus on cutting-edge materials for green energy and the environment. The scope of EcoMat is intentionally broad, including energy harvesting, storage and conversion, batteries and supercapacitors, energy systems and networks, fuel cells, piezo and treble electrics, water and air pollution control, hydrogen generation, etc. The articles can be immediately opened once published. We also have a rapid average publication speed. EcoMat has already published 10 issues online so far since it was launched in 2019, and the article publication charges are still waived until next year's end. Our ambition is to make a mark in material science and its adjacent fields of high academic impact. Here, I would also like to introduce a bit about our dedicated editorial team. Our editor-in-chief is Professor Zijian Zheng from Hong Kong PolyU. We have 4 associate editors who are Songbin Yun from Northwestern University, Sam In-sook from UNST from South Korea, Qiang Zhang from Tsinghua University. He is also our moderator today, and Huijun Zhao from Griffith University. We also have Dr. Law as our managing editor based in Hong Kong. He takes care of the journal's editorial daily work. The journal has already, sorry, could you please, yeah, thank you, Sammy. The journal has already been indexed by ESCI, DOAJ, and COS before. Today, particularly, I'm very pleased to share that EcoMat was just promoted to SCAE earlier this month, and we will receive our first impact factor in next year's Web of Science JCR. Thank you, the editorial team, board members, all the authors, reviewers, and the readers. Thank you, everyone, so much for your tremendous support. Last but not least, we welcome you to follow our social media accounts. Please scan the codes here, and you will find us on WeChat, LinkedIn, Facebook, and Twitter. We look forward to your prestigious submissions. Currently, we accept research articles, reviews, and highlights. Now, I'd like to hand over to Professor Zhang to start today's webinar. Please do not be shy to post your questions in this webinar. Thank you.
Thank you, Ms. Diao, for your good introduction on Journal of EcoMat. So we will shift to our introduction of the first speaker, Professor Wiley Li from Dalian Institute of Chemical Physics. Professor Wiley Li received his bachelor's degree from Xiamen University in 2009 and PhD degree from Dalian Institute of Chemical Physics, Chinese Academy of Science in 2014 under the supervision of Professor Han Li. He worked as a visiting research associate of Professor Duman's group at the University of Tokyo and in the Harvard Aviator School at the California Institute of Technology. He started his career as taking laboratory of catalysis in DICP as an associate professor in 2014, and from 2017, he is working as group leader of micro-nano photocatalysis and the photosynthesis research group in solar energy division of the DICP. He was promoted to be full professor in 2018 His research interest is mainly focused on photocatalysis of solar energy conversion. He has published many high-impact research results, and he won rare kinds of academic awards, including Young Scientist Prize at the International Congress of Catalysis, as well as the Rising Star in Catalysis of China. And now he is the vice chairman of the Hydrogen Energy Society of China. He's working as the editorial board of rare journals like Chinese Journal of Catalysis, Chinese Chemical Letters, and Journal of Applied Chemistry. Today, his topic was focusing on converting solar energy into chemical fuels via photocatalysis water splitting. Professor Li, please.
Okay, thank you. Thank you for Professor Zhang's introduction. Yeah, can you see my screen?
Yes, sure.
Okay, so okay, yeah. Thank you for Professor Zhang's kind introduction. And it is my great honor to have opportunity to give a presentation at the EcoMat webinar series. So my name is Renggui Li, and from Dalian Institute of Chemical Physics, Chinese Academy of Sciences. Today my topic is about the converting solar energy into chemical fuels via water splitting. So as we all know, the energy is the material basis of our human beings, and at present our global primary energy consumption is still dominated by the fossil fuels, such as coal, oil, and natural gas. And so the concentration of CO2 dioxide in the atmosphere is around 410 ppm. So this is mainly induced by the consumption of our fossil fuels. So it strongly requires our renewable energy, such as solar energy, for our sustainable world. So we know the solar energy is abundant, clean, and cheap, and the sun shines on Earth every day. So the annual average solar energy shining on the Earth exceeds around 170,000 terawatts. So this is much greater than the annual the primary energy consumption by for our world. So in a world, as long as 1 to 2 hours of solar energy can meet the annual world energy consumption. So this is from this comparison, we can see that we have a great power to utilize solar energy for our sustainable world. So this is the global solar energy distribution, and from here we can see that most of the countries in the world possess abundant solar energy resources, especially in Africa, America, Australia, and most of the Asian countries. So for solar energy conversion, there are many ways to convert solar energy for solar energy conversion. So traditionally, we all know the solar to thermal energy conversion, solar to biomass energy conversion, solar to electricity energy conversion. Today, I'd like to talk something about the solar to chemical energy conversion. And the solar to chemical energy enables to store solar energy in the form of chemicals for easy transportations and utilizations. So artificial photosynthesis actually is a process to mimic the nature photosynthesis. We all know in nature photosynthesis, CO2 and water can be converted into biomass and oxygen. And in artificial photosynthesis, we actually use a photocatalyst to convert the CO2 and water into some solar fuels. Actually, two important reactions are involved in artificial photosynthesis. The one, the water splitting to produce hydrogen and oxygen, and another reaction is the coupling of CO2 and water into chemicals. Actually, for this reaction, we can also it can also be divided into two half reactions. First, we generate the hydrogen from water splitting, and then the CO2 hydrogenation to synthesize chemicals. So we can see that most key reaction here is water splitting to produce hydrogen. Actually, if we can realize water splitting, very efficient water splitting using solar energy via the photocatalysis, photoelectrocatalysis, and also the electrocatalysis, we can get renewable hydrogen energy. And when we get renewable hydrogen energy, we can directly use as the hydrogen fuels, and it can also used in fuel cell. And the most important thing is the renewable hydrogen energy can be coupled with atmosphere CO2, and we can use a thermal catalysis process. This is the CO2 hydrogenation to generate methanol. And the methanol can be used as a platform, a molecule to further synthesize liquid fuels and also the chemicals. So this is the process that we name the liquid solar fuels or liquid sunshine. And in our lab, we also explored, so from the liquid solar fuels process, we can see the most key process is water splitting to generate hydrogen and also the CO2 hydrogenation. So in our lab, we mainly focus on the electrocatalysis, photocatalysis, and the photoelectrochemical catalysis to generate renewable hydrogen energy. And this is also example that we have explored a very efficient electrocatalyst for scalable water splitting in alkaline condition. And we established a scale of over 1,000 cubic meter volume per hour. So this is the largest. So this is now is the largest scale of solar water splitting so in China. And for CO2 hydrogenation, we also explored a very highly selective photocatalyst, highly selective catalyst. This is a solid solution catalyst containing the zinc oxide. So it can realize very efficient CO2 hydrogenation to synthesize methanol. So after we realized these two processes, we established an industrial demonstration in Lanzhou province, in Gansu province. So the demonstration containing 10 milliwatts solar station to generate electricity, and then we use our efficient electrocatalyst to generate the hydrogen. And we also combined the CO2 hydrogenation process to generate the methanol. And this scalable demonstration with a scale of 1,300 tons methanol per year. So this is also some pictures of our industrial demonstration for solar fuels production. And we know that the solar water splitting is a key process to realize the solar fuels production. And except for the electrocatalysis, so in our lab, we also focus on the photoelectrochemical reaction, water splitting, and also in photocatalysis. And today I'd like to talk something about the progress in photocatalytic water splitting. As we all know, in the photocatalysis process, we only need the photocatalyst to disperse in the solution, and this is a very simple process. And if we can get very efficient photocatalytic water splitting in the future, maybe this is a very promising solution to generate the hydrogen from solar water splitting. And in photocatalysis, actually, it is a very complicated process. So this cartoon shows the mechanism of photocatalytic water splitting on semiconductor photocatalyst. So generally, so when light is shined down, the photocatalysts were excited by the light radiation to generate electron in the hose. And the electron in the hose was separated and and transferred from the bulk to the surface of the photocatalyst. And in the surface, on the surface, the electrons was trapped by our reduction co-catalyst for hydrogen production, and the hose were trapped by oxidation co-catalyst for water oxidation. And the challenge of this reaction is it spans more than several timescales from light harvesting to transpiration to the surface catalytic reaction. So generally, electrons were generated at a time scale of femtosecond to picosecond. But the surface reaction almost take place at about microsecond to millisecond. So this is the challenge of this photocatalytic water splitting. And the whole solar to energy conversion efficiency was determined by the light harvesting efficiency, charge separation efficiency, and also the charge utilization efficiency. And the charge separation is a key process to connect the light harvesting and the surface reaction process. So this is a bottleneck in photocatalysis. So today I'd like to talk something about the strategies how to separate the photogenerated electron holes in photocatalysis. So just in several years ago in our lab, we found a very interesting phenomenon that the surface phase junction is very efficient to separate the photogenerated electron holes. So we all know that for TiO2, for example, for TiO2, the entities and the rutile are two typical phases in TiO2. But we found that a very interesting phenomenon that for a mixed entities rutile phase, so we found that when the surface junction was formed between entities rutile phase, we can get very remarkable improvement in photocatalytic water splitting performance, and which is greatly higher than the entities all rutile phases. So we also further investigated indicate that the surface phase junction formed between rutile and entities can play important roles in special charge separation. So as we all know, the difference between entities rutile is only very tiny difference exists between the entities rutile phase, but we found that only a very tiny difference can give a very remarkable enhancement in photocatalytic activity, only when we fabricated a very smooth interface between entities rutile phase. So this phenomenon can be further utilized in some other materials. For the gallium oxide, we can see that for the alpha phase gallium oxide, the activity water splitting activity is like that, and for a beta phase it is much lower. But when we deposit some entities of some beta phase on the on the alpha phase, we can see that the water splitting performance was greatly enhanced just by controlling the interface between the alpha and the beta phase. So this gives a very strong evidence that the surface phase junction is really a very efficient strategy to promote the photogenerated charge separation in this process. And we also use our timely resolved spectroscopy to further understand this process. And we found a very interesting phenomenon that a very fast charge separation process at a time scale of 3 to 6 picoseconds take place between the alpha phase and beta phase. So this is maybe the dominant reason that why the surface phase junction is very efficient in this system. It's because we have a very fast charge separation process take place between two phases. And we also further understand this process. We also demonstrated this spectral charge separation on a PC system. For example, for TiO2, we can very rationally control the photoanode to synthesize the photoanode like the type B, that is FTO entities rutile phase. And we can also construct a reverse structure like that. So that is FTO rutile entities. And we can also construct a mixed phases like this. And when we perform the PC water splitting performance, we can see that only for the type B, we can get a very high photocurrent density and also a very negative onset potential. And in this process, we can see that only the photogenerated electrons can only transfer from the rutile to entities phase, but not from entities to rutile. So this is also the evidence that the spectral charge separation takes place between at the interface of entities rutile phase. So we also measured the charge separation efficiency when a very smooth interface was formed between entities and rutile phase. We can get very high charge separation efficiency in this system. So the next question is, we still try to understand, is there how the charge separation take place on a single semiconductor without any phases? Because for the NTS rutile phase, it still have some structure difference for the NTS rutile. So we are considering how the charge separation take place on a single semiconductor without any junctions, without any surface junctions. So we use a beam-mass vanillate. This is very typical material in photocatalysis. So we use this material as our platform to understand how the charge separation take place. So the strategy we use is the in situ photochemical process. So we use the in situ photochemical probe reaction to probe the photogenerated electrodes in the holes in photocatalysis. For example, when we use some photoreduction deposition of some noble metals such as gold, platinum, and silver, we found that the reduction deposition of some noble metals only take place on the 010 surface of beam-mass vanillate. But when we performed some oxidation reaction, for example, the photo-oxidation deposition of lead oxide from lead ions, we can see that the photo-oxidation reaction will take place on the 110 surface, not on the 010 surface. So we know the reduction deposition is an electron-involved reaction, but the oxidation deposition is a hole-involved reaction. So we can see that from this result, we can see that the photogenerated electrodes and the holes can be separated onto different surface of a single semiconductor. So we also use some fluorescence imaging process to confirm this process. So based on the ball result, we can get a conclusion like that. So when the light shine on, the photogenerated electrodes and the holes can be separated at a micronanometer scale and on a single semiconductor. So then we proposed a special charge separation between different surfaces. And very recently, we also demonstrated this process on beam-mass vanillate with a very different morphology. We can see that we can also synthesize beam-mass vanillate with a cubic nanoplate, and we can also very precisely control the thickness of the nanoplate to tune this special charge separation property. And we can see that even when we change the thickness, we can realize the special charge separation on the different surface. The electrodes on the 040 surface, and the holes accumulated on the 200 surfaces. And the special charge separation property was very closely depended on the surface proportion. And actually, the matching degree of the charge collecting length and the crystal configuration is considered to be a major factor to determine the special charge separation between beam-mass vanillate. Now, we still want to understand how the driving force for the special charge separation between different surfaces. So we use a very homemade, specially resolved surface photovoltaic spectroscopy to perform for this beam-mass vanillate nanocrystal. So we measured the surface photovoltaic on the 010 to 110 surface of beam-mass vanillate. So we can see that the surface photovoltaic on the 110 surface is much stronger than on the 010 surface. So it means that the building electric field beneath the 010 to 110 phases show very great difference. And the building electric field caused by the surface band bending in the space charge region of 110 surface is much stronger than on the 010 phase. So this surface band bending can induce the photogenerated holes transfer from the 010 to 110 surface, and the electrons transfer in the opposite side. So this may be the reason why the special charge separation can take place on a single semiconductor. So as we can see, as we have demonstrated that the special charge separation can take place between different facets, But now the question is how to utilize this phenomenon, how to utilize this strategy to construct efficient photocatalyst. So in photocatalysis, we also need some co-catalyst. So generally we know because we know the reduction reaction and oxidation reaction are involved in the photocatalysis. So we generally require the reduction co-catalyst to accelerate the reduction reaction and the oxidation co-catalyst to promote the oxidation reaction. And the reaction rate was determined by the slowest one in reduction and oxidation reactions. So now the question is how to rationally deposit the reduction and oxidation co-catalyst on the semiconductor photocatalyst. So as we have demonstrated, electrons and holes are separated onto different surfaces. We know the electrons accumulated on 0, 1, 0 facet because the electrons are involved in the reduction reaction. So we need to deposit the reduction co-catalyst selectively on the 0, 1, 0 surface. And we can also require the oxidation co-catalyst only selectively deposit on the 1, 1, 0 surface. So in this case, we can specially separate the reduction and the oxidation active sites on a semiconductor. So this is a result. We still use the Binder's vanillate as an example. We can see that when we control the condition of photo deposition, in situ photochemical deposition, we can see that as with the cobalt oxide and manganese oxide are typical water oxidation co-catalyst in photocatalysis. So we can rationally control the deposition of cobalt oxide and manganese oxide on 110 surface, very selectively on 110 surface. And we can also selectively deposit the platinum nanoparticles on the 010 surface, which is a reduction co-catalyst. So we can see that we can separate the reduction co-catalyst and oxidation co-catalyst onto different surfaces of a semiconductor. And this is the activity of when we selectively deposit the co-catalyst on the surface. And we can see that the water oxidation performance was remarkably improvement when we selectively distributed the co-catalyst onto surface, which is around 100 times higher than Binder's vanillate. But traditionally, when we randomly distributed the co-catalyst on every surfaces, we can see the activity was still at a very low level. And we still further measured to understand why the co-catalyst why the selectively distributed co-catalyst give a very remarkable improvement in photocatalytic water splitting performance. And we also still use a special result of the surface volume spectroscopy to measure the interface. So we found that when the co-catalyst was selectively deposited on the surface, it not only provided the active sites for the surface reaction, but it also changed to promote the charge separation process, which provide a much stronger charge separation driving force, so that the more electron and holes can be separated for surface reactions. So this is the reason why the selective distributed co-catalyst can give a remarkable improvement in photocatalytic water splitting. And actually, spectral transpiration between different surfaces is a very general phenomenon in many kinds of semiconductors, such as cobalt oxide and also TiO2 and rutile phase TiO2. We can also see that when we selectively deposit the reduction and oxidation co-catalyst onto different surfaces, the photocatalytic performance was greatly improved when we use the spectral transpiration property. So, based on the previous results, we are still thinking about another challenge question is, because for the Binder's vanillate, it is a monocanonic phase. For TiO2, it is also a low symmetric structure. So the question is how to separate the photogenerated electron holes for a high symmetric nanocrystal. Because for a high symmetric structure, a nanocrystal, it will easily to expose all the equivalent surface, not the different surface. But for the equivalent surface, it is very difficult to separate electron and holes because all the surface properties are almost the same. So this is the question that we so this is also a very challenging question. So how to separate the electron and holes on a high symmetry nanocrystal? So our strategy is like that. So we use a strontium titanate is a cubic phase semiconductor, and also very widely used in photocatalysis. And when we synthesize the strontium titanate, we found that it's very easy to synthesize morphology like that. All the six surfaces are the same. So as we cannot change the crystal structure of strontium titanate, but it is possible to change the morphology, the symmetry of the morphology. So, for example, when we cut all the edges of this material, we can get morphology from a cubic phase to this kind of phase. But for this phase, the exposed phases is 001 and 110. But when we do the theoretical calculation, we found that the surface energy of 110 is almost comparable with 001. So it means that when we control the synthesized condition, maybe it is very possible to expose the surface of 110 and 001. So we use some chemical process to synthesize the morphology, and we can see that we can successfully realize the morphology change from the from this kind of morphology to this kind of morphology. For the cubic phase morphology, we can see that the electron and holes are randomly distributed on every surface, as all the surface properties are the same. But for this kind of morphology, a very interesting phenomenon is that when we perform the electron involved the reduction reaction, we can see that a reduction reaction will take place on the 001 surface. But for the oxidation reaction, we can see the oxidation reaction will take place on the 110 surface. So this is very interesting because we can, when we change the morphology, we can realize the special charge separation between 001 and 110 surface and to nanometer scale. So this is the time scale. So the scale bar here is 200 nanometers. So when we especially separated reduction and oxidation active sites, we can see that the water oxidation, the water speeding performance was very greatly improved. And so in this system, I think there are two advantages. One is when we use a morphology tailoring strategy, we improve the charge separation efficiency. Another advantage here is when we separated the hydrogen production and oxidation evolution process onto different surfaces, the reverse reaction between the hydrogen and the oxygen to form water was greatly inhibited in this system. So this is the reverse reaction in photocatalysis is also a very key challenge. But when we use morphology tailoring strategy, we can also block the reverse reaction just to change the morphology here. So very recently, Professor Domo from the University of Tokyo also used our similar strategy to deposit the reduction and oxidation co-catalyst on aluminum doped strontium titanate and realize quantum efficiency of 100%. So this is very remarkable result in photocatalysis. And we still want to know how to greatly improve the special charge separation property, because the surface polarity also very interesting is also a very intrinsic property in most of the semiconductors. But how to utilize the surface polarity to introduce an intrinsic charge separation driving force in photocatalysis is still not very clear. So we use the gallium nitride as a semiconductor as an example. So for gallium nitride, we can fabricate the gallium nitride on the substrate to expose all the 001 surface, which is the polar surface of a gallium nitride. When we performed the photocatalytic activity, we found that only the polar surface was exposed, the activity was still not very high. So based on the understanding in special charge separation between different surfaces, so we are aiming to expose the non-polar surface, which is perpendicular to the polar surface. So we use some chemical etching process to fabricate the co-exposure of the polar surface, non-polar surface on gallium nitride. So this is the SEM images of the gallium nitride nanorods. We can see that we can rationally control the surface, the exposed polar surface and non-polar surface on gallium nitride. And for gallium nitride surface, we can see we also use the photo deposition process to trap the electron host. So we can see that the photo reduction deposition of some noble metals only take place on the non-polar surface, but the oxidation deposition of some manganese oxide and the cobalt oxide only take place on the polar surface. So we can realize the deposition of manganese oxide of the reduction co-catalyst and oxidation co-catalyst separated onto different surfaces. And this is water splitting performance. We can see that when we separate the reduction oxidation co-catalyst onto different surfaces, the water splitting performance was greatly improved, and the quantum efficiency was exceeds more than 10%. But for the only for the polar surface, the activity was very, very low. And we also measured the charge separation efficiency in this system, and we can see that the charge separation efficiency between the polar surface and the non-polar surface can exceed more than 80%. So this is very high quantum efficiency in photocatalysis. And we still use some special result surface photowattage spectroscopy to measure the surface photowattage between the polar surface and non-polar surface. And we can see that the surface photowattage give a very great difference. And the surface bending of the polar surface is stronger than the non-polar surface, and which may be the driving force for the spectral transpiration between the polar and non-polar surface. So in the last part, I would like to discuss a very broader question, that is, as we all know, in the process of photocatalysis water splitting, people are still attempting to achieve a scalable solid water splitting using a particular photocatalyst. So although the activity now is still not very high, so when in the future when the efficiency was improved, how to realize a scalable solid water splitting? As we all know, for the overall water splitting, the hydrogen and oxygen were produced simultaneously, and when the hydrogen and oxygen are mixed together, it is very it can bring the safety risk, and also another challenge is it's very difficult to separate the electron to separate the hydrogen and oxygen in this process, and another challenge is reverse reaction between the hydrogen and oxygen to form water is also a very, very big challenge. So in our opinion, all these challenges very greatly blocked the process of scalable solid water splitting. So also actually, so here this is example from the Professor Doma's group in University of Tokyo. So they proposed for the water splitting pedal that is use a strontium titanate photocatalyst, and they realized the solid to hydrogen efficiency around 0.7 to 1%. So very recently, they also established a scalable solid water splitting panel using strontium titanate photocatalyst. But now the very big challenge in this process is also the separation of hydrogen and oxygen. And separation of hydrogen and oxygen is a very big challenge, and also it is not a cost-effective process. So in our lab, so we are trying to answer this question. So if there is possible to separate hydrogen and oxygen in principle, and we know the natural photosynthesis is the very largest storage process on the Earth. And also we also use this process to plant crops in large scale. And in this process, the initial reaction is a water splitting reaction. So initially, the water was oxidized by PS2, and to evoke the oxygen in the atmosphere, and the electrons was captured. Electron energy was captured to the for the CO2 fixation process. So in this process, we know the water splitting was take place, water splitting reaction take place, but we don't need to collect hydrogen oxygen, and we don't need to separate the hydrogen oxygen. So use this process. So we propose a model like that. So we namely the hydrogen farm. So we use a photocatalyst to realize the water oxidation process first to produce the oxygen, and then the oxygen was evaporated in the atmosphere. And in this process, we capture the solar energy, use electronic medias, and then the electron medias can be very easy to transport and storage, so that and this is very easy to transport. When we need when we need hydrogen energy, we can use another reaction to produce a hydrogen and in the presence of the electron medias. So this is a very so in this process we can separate the hydrogen oxygen evolution in space, and we don't need to separate hydrogen oxygen in the gas mixture. So this is very easy to separate hydrogen oxygen. And another advantage is this the solar energy capture process can be operated in the open air without sealed system. So this is very easy for the scale-up applications. So to realize this process, we need to encounter two challenges. One is very efficient water oxidation catalyst in the presence of the electron medias. Another is a reverse reaction between electron medias, because when the water was oxidized here, the electron medias were reduced. But when the electron media was reduced, it is the reduced electron medias was exists in the solution. And in this case, the oxidation of the electron medias is also a competing reaction for the water oxidation process. So this is why we need to block the reverse reaction in this process. So the first challenge is how to realize the efficient water oxidation process. So we, based on the understanding of the special charge separation between different phases, we can precisely control the surface configuration between the 0, 0, 1, and 1, 1, 0 surface on Benjamin's magnetic catalyst. We can see that the water oxidation activity was closely related with the surface configuration, and we can realize the very efficient water oxidation with a quantum efficiency of over 60% for in the presence of iron 3, iron 2 plus, when we use iron 3, iron 2 plus and the sharp medias. So this is the first challenge. For another is a reverse reaction. So we know that, for example, we still use when we use iron 3, iron 2 plus as our electron medias, we found that when we rationally control the morphology, we can realize the very 100% of the conversion, iron 3 plus conversion on the very regular Benjamin's magnet nanocrystal. But when the morphology was not very good, we can see the very severe reverse reaction take place. So we still further understand this process. So the mechanism is like that. We know that when the water oxidation reaction takes place, the iron 3 was reduced to iron 2 plus, but iron 2 plus is a positive charged, But the reverse reaction for iron 2 plus to iron 3 plus should be initiated by the photogenerated host. But the host is also a positive charge on the 110 surface. So in this case, when during the water oxidation process, the iron 3 was reduced to iron 2 plus, but iron 2 plus is very difficult to approach the 110 surface for the reverse reaction. So this is why when we rationally control the morphology, we can greatly block the reverse reaction in this system. But when we use another electron medias for the iron cyanide, so this is negative charge ion. When we use a negative charge ion, we can see very severe reverse reaction take place. So this is very great. This is also evidence that why the reverse reaction can be greatly blocked on this system. And so we still further realize the blocking and reverse reaction via special charge separation onto some other materials. For example, the bismuth tungstenate is also a very typical photocatalysis, photocatalyst in photocatalysis. And so we can see that the special charge separation can block the reverse reaction when we rationally control morphology. So after we capture solid energy, use the photo-oxidation process. So we can also use another subsystem that is electrocatalysis cell to convert the ion 2 plus into ion 3 into ion 3 plus. In this process, we can collect the hydrogen. You can collect the hydrogen captured by the solid energy. So this is also the system we established. So when we realize we developed a very efficient water oxidation catalyst use a special charge separation property, and we also established a scalable solid water splitting system like that. So the areas around 10 square meters and on the tops of our buildings, and calculated overall solid to hydrogen efficiency of this system exceeds 1.8%. So this is still the highest efficiency in photocatalysis. And previously, the Professor Domin reported that we use a stratum titanate catalyst, the efficiencies are less than 1%. So this demonstration gives a very promised solution that we can realize the special charge. We can realize the scalable solid water splitting when we better understand the special charge separation property and also use our hydrogen farm process. So in the future, we still need to greatly improve this solid to hydrogen efficiency in hydrogen farm process. So one challenge is for bismuth friendly, the light absorption range is still not very good. So it is better to expand the light harvesting range for the catalyst from around 500 nanometers to even 600 nanometers to even 700 nanometers. When we expand the light harvesting ranges, we can greatly improve the efficiency, the light harvesting efficiency in this process. And another key process is the electron emitters. So we use ion 3, ion 2 plus in this system, but actually ion 3, ion 2 plus is still not very good shot emitters. And the chemical potential of this shot ion is too high. So it is better to reduce the chemical potential of the electron emitters to approach the zero. So this maybe is also the very it's also the strategy that we improve the solid to hydrogen efficiency in hydrogen farm process. So this is still highly demanding to improve the efficiencies when we have a very efficient catalyst with a very good light harvesting and also very suitable chemical potentials. And we are still working on the water oxidation catalyst that can be used in hydrogen farm process. Actually, we explored a series of materials. For example, bismuth tungstate oxychloride is also a very efficient catalyst that can be used in as the water oxidation catalyst in hydrogen farm process. But now the efficiency is still not very good, and we're still working on how to improve it. So now I'd like to give a very short summary of my presentation. And the solid water splitting for hydrogen production is also a very promising solution to face the energy and environment issues. And we have very different strategies: photocatalysis, photoelectrocatalysis, and also the electrocatalysis. And in photocatalysis, the photogenetic charge separation is the key and bottleneck in process. And the charge separation strategies like the special charge separation between different surfaces and also surface polarities have been demonstrated to be a very general and efficient strategy. And we also, in our lab, we demonstrate the liquid solar fuse production. We're combining the solar hydrogen production and the CO2 hydrogenation, and which have been demonstrated in industrial. And I believe that it will play a very significant role in the zero emission world in the future. And in the future, we I think the solar powers world is not a dream, and it can be realized in the near future. Finally, I would like to thank the Professor Kan Li, who's given very strong support to my research, and also would also like to thank some collaborators and our PhD student, and also financial support. And finally, thanks for attention. Any questions and comments are welcome. Thank you.
Yeah, Professor Li, thank you very much for your on photocatalysis. I have seen a couple of questions about. The first one was focusing on regarding the dual co-catalyst strategy. What criteria should be considered when selecting the co-catalyst? Are there any green candidates?
Yeah, so I think this is a very good question. So can you see my screen?
Yeah, I can't see your screen now.
Oh, I'm sorry. So okay. Now can you see my screen?
Okay, good.
Okay, now okay. So actually, co-catalyst is very important. So now our key is how to deposit the co-catalyst selectively on the right surface, not randomly distributed on every surface. So because we need the reduction co-catalyst to participate in the reduction reaction. Oxidation co-catalyst participate in oxidation reaction. But when the co-catalysts were randomly distributed on every surface, for example, reduction co-catalyst on the oxidation surface, it can greatly induce the charge recombination process. So we need to separate them. So I think the key is to selectively consider the charge separation, together consider charge separation in the co-catalyst, so that we can rationally deposit the reduction and oxidation co-catalyst on the right surface, on the right sides. So this is my answer.
Good. So we shift to the second questions. Considering the synthetic difficulty, catalytic activity, and separation efficiency, what is the ideal size for the nanocrystal dual co-catalyst used for morphology tailoring?
Okay, so the question is, what is the co-catalyst size, right?
Yes.
The co-catalyst size here. So actually, co-catalyst size is very important. So so in our process, we can rationally control the co-catalyst size. For example, when we deposit the co-catalyst with photoinstituted photochemical deposition process, so we can control the concentration of the precursor, and also we can control light intensity and also the light wavelengths to very precisely control the nanoparticles to optimize the co-catalyst size in photocatalytic water splitting. So we should optimize the co-catalyst deposition for in photocatalysis, and we can control the light intensity in the co-catalytic precursor, and also we can control the light wavelengths so that we can optimize the conditions. Okay.
Good. So we shift to the third questions. You mentioned a few times to achieve scalable solid water splitting. From a commercial point of view, when do you predict solid water splitting to become an affordable way to produce fuel? What are the limiting factors?
So you mean the electrocatalysis or photocatalysis?
Solid water splitting.
Yeah, solid water splitting using electrocatalysis, a scalable. So you mean the hydrogen farm process, all the previous all the industrial.
Yeah,
so
I think he is interested in the solid water splitting in a scalable way. How to become an affordable way to produce water fuel in large scale. What's limiting the?
Okay, so the question is, I think the question maybe is, so the reader is concerned on the scalable water splitting, solid water splitting use this process. So exactly. The motivation of this process is, so we know that the separation of hydrogen and oxygen were difficult in water splitting, and actually because when the hydrogen and oxygen was generated simultaneously, we need a sealed up system, not an open system. So it is not very easy for the large scale application. So this is why we learned from nature. We proposed a process like that. So in this process, the water oxidation for the large scale solid energy capture, only the oxidation was produced without hydrogen. And in this process, we can operate it in the open air without sealed system. But in this process, energy was captured. But energy was captured using electron mediums, and when the energy was captured using electron medium, it can be very easily to transport in the storage. So for storage, so when we need some hydrogen energy, we can use another subsystem. We can use for example, electrocatalytic cell to generate hydrogen. And in this process, we only need a very small bias to oxidize the electron emitted from a low state to a high state. And actually, in this process, oxidation reaction is the oxidation of electron emitted, not oxidation of water. And in water electrocatalysis, the challenge is the water oxidation needs a very high overpotential. But in this process, we only need to overcome the thermodynamic potential, not and this is only need a very small bias, not very. So this is very easy to realize. So in this process, we can separate the hydrogen and oxygen separately, and this is very easy to be utilized in a large scale. Okay.
Okay, thank you. So the final questions for the talk is about the degradation. Degradation has always been a major concern for catalysts. What is the general lifespan of your catalyst, and how do you prevent the degradation of your catalyst?
Okay, it's also a very good question. So I think because in photoelectric catalysis, Bismuth vanillate is very easy to be during the process. Actually, in photocatalysis, so we use the bismuth vanillate catalyst. It's pretty stable, and we operated the bismuth vanillate on the sunlight radiation for more than 7 months. It is still quite stable. And but the bismuth vanillate is not very stable in PC water splitting process. And when we applied in PC, we need a bias. When we applied another bias, it is very easy to destroy the bismuth vanillate and also have some interface issue. But in photocatalysis, bismuth vanillate is quite stable, and it also so now we have been use this material to operate it on the sunlight radiation for several months. It is quite stable. So this degradation is still not a big issue in this system.
Okay, thank you, Professor Wiley Li, for your clear answer to all questions. So due to the time limitation, I have to stop the discussion on your talk for word photocatalytic splitting. So thank you.
Thank you, Professor Zhang.
Okay, so we move to the next speaker from Professor Aizun Li on design of efficient catalysts for carbon dioxide reduction. Professor Aizun Li is working at Queensland University in Australia. He obtained his PhD in 2002 from Fudan University. He was awarded both Australian Research Council Future and Queensland Elizabeth II Fellowship. ARC Future is very important for the faculties in Australia. His research lies at the interface of physics, chemistry, and engineering, focusing on the development of innovative materials for electronics, energy, and environmental application using advanced theoretical modeling approach. He has published over 300 papers and is selected as a highly cited researcher by Clear Analytics. So, Professor Liu, it's your time to give your talk on carbon dioxide reduction.
Okay, thanks, Professor Zhang. To share the slide.
Sorry, I can't see your slide now. I see that a few minutes ago, but now it's down for sharing.
Yeah, I need to share my slides.
Okay.
Sorry.
I can hear your voice very clearly.
Okay. Can you see the slides?
Okay, it's working now. Good, great.
Okay, so sound is also okay.
Good.
Okay. Thanks, Professor Zhang, for the kind introduction. Hello, everyone. Good evening from Australia. It's my great honor to be here. First, many thanks to Professor Zhang for the invitation and Dr. Low for the organize this webinar. This picture shown in this slide is a bird's eye view of the city of Brisbane, Australia. The main campus of Queensland University of Technology is located somewhere here. Yeah, I need to. Somewhere here, yeah. So the location is really good. So our university actually is a small and young university, and it's ranked as the top of 50 young university under the 50 years old. What I'm going to talk today is about the design of emerging catalysts for carbon dioxide reduction. And my research in Australia actually is purely theoretical or computational, and focusing on the exploration of the chemistry and the physics in material science with potential applications in energy and electronics. I'm not sure I'm the first speaker from the theoretical side to present in the EcoMat webinar. And as you can see from this slide, my research covers a wide range of topics. Today's main topic is carbon dioxide reduction, and actually it's one of my research focus. I have been working on the carbon dioxide reduction for some time, actually, yeah. But we don't have too much works on this topic, because the reason is we worked on the theoretical side, and also I need a very small theoretical research group in Australia. So normally there are only one student work on the project of carbon dioxide reduction, and there are sometimes between from 1 to 3 years there's no students work on this project. So I stopped this project for a while. So I believe most audience here probably from the experiment side. Me to talk about a little bit more about my theoretical research. It might give you some idea of what does theoretical research looks like, how theoretical research contributes to the experiment development. My research focuses three aspects. The first one is called electronic structure engineering. And materials properties are in principle determined by the electronic structure. And if you give them materials, we can calculate the electronic structure. We can tell you whether this materials is specific for some applications. And the question is, we can engineer the materials and electronic structure, but then we can modulate the materials properties. For example, in this work, we use the substrate as an electrostatic gate to modify the graphene's properties. And this is for the electronics application. In another work, we duped 2D materials with single atoms to make it become an effective single atom catalyst or catalyze the nitrogen fixation reaction. Our research also provides strong support to the experiments. For example, we have the experiment to explain why interfacing the defect graphene with the layered double hydroxide can be efficient for water splitting. In another examples, we have an experiment to explain the anti-graphene bilayer can be effective for water desalination. Yeah, my research we also predict some new materials for experiment to verify. In 2016, we predict a stable 2D borohydride nanosheet, and the materials was synthesized in 2017. In this year, a new type of hydrogenated boron was synthesized on a metal substrate, this work was published in Science just a few months ago. Let's back to my today's main topic, design of emerging catalyst for carbon dioxide reduction. And my talk actually is purely from a computational perspective. It's based on my personal experience and my personal understanding in the field of carbon dioxide reduction. Three topics will be focused. First, I will talk about a little bit about exploring carbon dioxide reduction from the single atoms to the precise number of atoms. The second topic will be focused on tuning carbon dioxide reduction by engineering atomic coordination environment. And this is basically for the copper, well-studied electrocatalyst, the copper-based catalyst. The final topic will be on boosting carbon dioxide reduction through the interface engineering. During the talk, I will also discuss include some experiment for discussion. For carbon emission, I do not need to give too much background because it's well known to the public. Carbon emission actually always appear on the newspaper headline in many countries. From this figure, you can see the global energy demand is rising with the years. And coal, oil and gas are the major energy resource for the fuel cells. And in some day, the fuel cells will be used up. Here is the figure. You can see here, it is predicted that the fossil fuels such as oil and gas will be used up by around 2051 and 2061. The burning the fossil fuels also increase the greenhouse gas emission, which is the main cause of the global warming and climate change. In this figure, you can see here among the greenhouse gas, all the greenhouse gas contributed to the climate change. You can see the carbon dioxide actually account for the larger part of contribution. It's at least 60%. I saw different numbers, 64 or 76% on the website. So carbon dioxide is the major contributor to the climate change. So it's important to note that the carbon dioxide fraction in the air, is increasing with the year, substantially increased with the years. You can see from this figure, particularly in 2020. The United Nations Climate Change Conference was held in last month at Glasgow. The COP26, in the COP26, some agreement has reached, and some goals have been set up. So the first, for example, let's increase in global temperature to well below 2 degrees above the pre-industrial levels, and pursuing an effort to limit it to the 1.5 degree. And it should be noted the pre-industrial level actually is the Paris Agreement temperature goal. Is set at 2 degrees. The deep and rapid sustained reduction of greenhouse gas emission, including the reduction of global carbon dioxide emission by 45% by 2030 relative to the 2010 level, and to net zero around the mid-century. COP26 agreeing that coal is the single biggest contributor to the climate change. Over 140 countries promise to reach net zero emissions. So for carbon dioxide reduction, it's important for us to understand the carbon cycle. In the natural carbon cycle, the plants capture the atmospheric carbon dioxide, and under the sunlight, and release the oxygen and convert the carbon dioxide into the glucose molecules and store the energy. So the plants and the animal organisms will suffer a decay, and then waste product and the dead organisms will bury underground to produce the fossil fuels, and the fossil fuels will be used by the human beings and in the industry or in car emission, and also release carbon dioxide back to the air. So this process is called natural carbon cycle. It's very slow because of the fossil fuels. The generation of fossil fuels will take millions of years. So we did a chemical carbon cycle. Chemical cycle, different from a natural carbon cycle, is the carbon dioxide is captured in the factory and then stored it. And by using the renewable energy to drive water splitting to produce hydrogen, and then we can hydrogenate carbon dioxide into the methanol and also other hydrogen carbons. This can be used as fuels to replace the fossil fuels. And when use these fuels, we also generate the carbon dioxide back to the carbon in the air. As compared to the natural carbon cycle, the chemical carbon cycle is relatively fast, which is urgently needed. I started my project, carbon dioxide project, in 2010, following the United States government drops the funding for hydrogen fuel cell cars, then moved the research to the battery research in 2009. Previously, I have been working on the hydrogen storage for a long time, while there's no fund to support my hydrogen storage research. So I changed the molecule from the hydrogen to the carbon dioxide in 2010. And due to my experience in the hydrogen storage, I entered the carbon dioxide capture, this field, the field of carbon dioxide capture, very quickly. Yeah, we published the work immediately in 2010. Here are some examples I choose from my research on the topic of carbon dioxide capture and separations. So in this work, we use the charged boron nitride nanostructure to capture carbon dioxide, and then to separate the carbon dioxide with the nitrogen. Is the mixture of it's actually flow gas. So this approach actually is basically an electrochemical approach, because we demonstrated the carbon dioxide capture and release is simply controlled by the charging and discharging, and which is similar to the electrochemical approach. In another work, we propose to use the electrical field to drive carbon dioxide capture, and also the separating the carbon dioxide and the nitrogen. The mixture of carbon dioxide and nitrogen actually is a flow gas I mentioned before. It's the main product from the coal-fired power plants. At that time, the carbon dioxide capture and storage are more focused than the carbon dioxide reduction. There are not so many works on the topic of carbon dioxide reduction around 2010. So, however, there's a challenge for carbon dioxide capture and storage. We think we agree that it's very expensive for most coal-fired power stations. It's very expensive. So the best choice would be to develop a catalyst for carbon dioxide reduction. So the carbon dioxide can be captured and then converted to the alternative liquid fuel cell, such as CH4, C2H2, and C2H4, and methanol and ethanol, formic acid, etc. And via the hydrogenation approach, electrochemical approach, or the photochemical approach. And then the methanol and the ethanol and the hydrogen carbon molecules can be used as fuels to replace the fossil fuels. However, the carbon dioxide is highly inert. The breaking of carbon-oxygen bond generally require high energy cost. Many catalytic approaches have been developed for carbon dioxide reduction. And there are some are listed here: electrocatalysis and photocatalysis. The thermal approach and the photothermal approach, and the enzymatic catalysis approach. And currently, the most hottest topic, most research focused on electrocatalysis and photocatalysis, in particularly electrocatalysis. For the enzymatic catalysis, there's a big progress this year by the Chinese scientists using the enzyme to convert the carbon dioxide into the starch. This is regarded as a big progress. I will not talk about this approach, mainly focus on the electrocatalysis and photocatalysis. The electrocatalysis and photocatalysis actually are driven by the electricity here, and also by the light, mostly visible light. It's better to use the visible light. As you can see from the picture here, the products for the carbon dioxide reduction, there are many different products. You can see range from the CO, formic acid, HCHO, CH4, C2H4, methanol, and ethanol, C2H6. There are many different products. And the challenge is currently the challenge is the selectivity. It's very hard to generate a single product, because there are many different reaction pathways needed to the many different products. So the selectivity is a very big challenge. Another thing is the traditional transition metal catalyst always has the linear scaling relationship, but this is the bottom letter to overcome. Because the the binding of the reaction intermediate on the catalyst, the binding energy follow the conventional linear scalar relationship. So it's very hard to optimize the binding free energy, So it's hard to further improve the carbon dioxide reduction performance. That's also a big challenge. Another big challenge is it's better to produce the high value, the multi-carbon product, for example, C2 plus product. And this is also the big challenge. And currently, single atom catalysis is a very hot topic in the field of catalysis. And single atom catalysis was first reported by Professor Zhang at Dalian Institute of Chemical Physics. And this work published in Nature Chemistry actually is a landmark paper and introduce a new paradigm for the in the field of heterogeneous catalysis. So in 2016, we started to apply the single atom catalysis into the carbon dioxide reduction. The first materials we choose is graphite carbon nitride. Why choose graphite carbon nitride? Because it has been demonstrated in experiment is photochemically active for like water splitting, can be used as a photocatalyst. And also the graphite carbon nitride, you can see from this picture, there's many the pores here. It's porous. So it can be easily stabilize the transition matter. If loaded, the transition matter, it is an accommodated transition matter from the single atom catalyst. We found the platinum and the platinum doped graphite carbon nitride possess enhanced visible light response, also demonstrated favorable thermodynamics and kinetics for carbon dioxide reduction under visible light. There's another example I choose from my research on a single atom catalysis. We use another 2D materials. It's called a 2D boron nanosheet. It's synthesized by experiment very recently. It's not very recent. It's in 2016, around 2017. And similar to the gravity carbon nitride, the boron nanosheet is also porous. Then we can know that the transition matter can be stabilized on the pore here. And then we're using the high throughput computational screening approach to find the best single atom catalyst to support on the 2D boron nanosheet for carbon dioxide reduction. We find that vanadium doped single atom catalyst is the best for the carbon dioxide reduction. This is a very recent work. We loading the single, but through the collaboration with my colleagues at QUT, we load a single transition metal on the ferroelectric indium satellite model. The indium satellite model is ferroelectric with the electron, the electrical polarization. So actually, the indium satellite model is not very stable. It's not very stable. It has been synthesized experiment, maybe not very stable. But here we provide an interesting concept, a new idea, and we can use in the ferroelectric switch to control the single atom catalysis. Because the ferroelectric materials has electrical polarization, we can use in the ferroelectric switch can control the single atoms catalysis. Metallic organic framework also is a hot material to be used for the gas storage and gas separation. So we use the high throughput computational screen approach to find the best metallic organic framework. And in this metallic organic framework, you can see here the transition metal coordinates with the 4 nitrogen atoms. Normally, the metallic organic framework transition metal coordinates for some morph coordinate with the carbon oxygen atoms or the sulfur atoms. For this morphs we are using is coordinate with the nitrogen atoms. And so basically the structure is like a TM-iron4 based morph structure. We're using a computer scratch to find the best one. The best one we find is the iron and nitrogen 4. Yeah, we also predict these materials. The side reaction for the HER can be also avoided. So here I list one experiment published in Nature Nano this year by Chinese scientists. They show they demonstrate use the single atom catalyst for carbon dioxide reduction using a single alloy catalyst for the carbon dioxide reduction. And now it's the single atom catalyst has been widely used for the carbon dioxide reduction. It has demonstrated great potential for reduction of carbon dioxide to CO, formic acid, and methanol or CH4. And this product contains only one carbon atom. They call C1 product. When we, in order to produce the high-valued multi-carbon products, so normally for the formation of the multi-carbon products require the carbon coupling. In this case, probably it's better to have more catalytic active site needed, catalytic site. So it's important for us to try to go beyond the single atom catalyst by using precise number of atoms catalysis instead of the single atom catalyst. So here one example, I designed a carbon dioxide reduction catalyst beyond the single atoms. The materials we choose is graphene. Has been also synthesized by the experiment. We studied the size effect of the cluster different atoms loaded on the graphene, because the graphene also have the pores. the power here. So we load the ion cluster from a size from 1 to 4 atoms on the power here, and then we calculate do calculations to predict the carbon dioxide reduction performance. We found that the selectivity and the activity can be tuned by the cluster size, by the cluster size here. And the dimer catalysis, the double atom, and also the triple atom ion catalysis, even outperform the single atom catalyst for carbon dioxide reduction. Here's another example I use in the double atoms. Here, we introduce the metal and the non-metal coupling atomic pair because they possess different electroactivity. So it's asymmetric. The asymmetric, we found the asymmetric copper and boron atomic pair because the pair with the d orbital and the p orbital coupling can promote the CO dimerization, and then can lead to the high valued C2 product. Sorry, C2 product. You can see here is C2 product. Here's another work we designed the copper string cluster support on the 2D C2 ion for carbon dioxide reduction. We found that the C2 string on the 2D C2 ion can form a Schottky barrier to promote the charge transfer between them. And then the catalyst, can activize the multi-Schottky catalyst for the carbon dioxide reduction, and can lead to the production of the ion propanol. Yeah, it's a C-string product, actually, C-string product. The important thing is recent experiment demonstrated the use of the clusters copper string to support on the carbon materials demonstrate the highest performance for carbon dioxide reduction to convert it to the final product is enhancer. So now the experiment in the theoretical work, the mostly well-studied catalyst for carbon dioxide reduction is copper. The copper, because the copper is the only heterogeneous carbon dioxide reduction catalyst that produce hydrocarbon molecules. And the pioneer work published in 1985 is quite early, very early. Yeah. And there's a good review paper also published recently in the Chemical Review. You can find more details on this topic. The copper is also the only family of the catalyst that can reduce carbon dioxide to multi-carbon molecules with the significant Faradic efficiency and current density. But however, there are also the major challenges: selectivity toward a single product and the generation of high value added multi-carbon product. This is the major challenges. So because of the selectivity and the activity, so the many current experiment and mostly are experimental work, but not so much theoretical work reported on the copper-based catalyst. So within the experiment, many focus on and try to modify the atomic coordination environment, the reaction environment of the copper around the copper atoms. For example, in this work, using the dopant, the boron, at the subsurface to induce the electron nuclearization to drive the carbon dioxide reduction to the C2 product. Here, they're using the subsurface boron to tune the atomic coordination environment, reaction environment of the copper. In the second paper published in the Nature, the experiment using the molecule to tune the carbon dioxide to the C2H4 conversion. They also change the absorption environment, also enhance the stability. The third experiment I listed here is about try to use the high index surface, the copper surface, and also the step surface of the copper, because the coordination number is different. Also change the reaction environment for the copper, around the copper. And the final work I listed here is using the bimetrical copper aluminum bimetal alloys to it's demonstrated this alloys can have achieved the highest activity and selectivity for the carbon dioxide reduction. So recently, we also try to do something. This topic is currently one of my students is working on this topic. It's the main focus. We try to tune the catalysis performance of the copper by controlling the atomic composition or also atomic ratio. This recent work, we haven't published this work, but we got some interesting results here. For the carbon dioxide reduction, the very early experiment here, I solely focus on the industrial catalyst for the methanol synthesis. I need to mention the industrial catalyst for the methanol synthesis. You can see from the science paper published in Science, they try to understand why this catalyst is the copper and the zinc oxide and aluminum oxide mixed together and can be effective for the methanol synthesis to understand why. Now they reach the agreeing that they reach the conclusion that it's basically the enhanced performance is due to the tuning the selectivity of carbon dioxide hydrogenation reaction at the metal oxide interface. Also, the recent science paper also proposed the modify the copper's catalytic activity by using the interface. So all this experiment works emphasize the role of materials interface. The material interface play an important role here. So we also carry out some work to design some interface to catalyze the carbon dioxide reduction here. The interface we demonstrate here is published in the EcoMat. Thanks for the Professor Zhao, editor Professor Zhao invited me to submit to the special issue for the carbon dioxide. I submit this one to the EcoMat. We designed an interface called the graphene and the carbon boron nitride interface. These materials have been synthesized in experiment. It's called graphene and boron nitride heterostructure. We demonstrated, we used the interface and we found that it can facilitate the carbon dioxide conversion with very high activity and selectivity. But also the curvature. If we have a curvature, also can further tune the activity and selectivity. In another work, we also design an interface to promote the carbon dioxide reduction. But for this work, we mainly focus on the carbon monoxide reduction. And because it's based on the motivation for studying the carbon monoxide reduction, because recently 2 science papers demonstrated the reduction of carbon dioxide to carbon monoxide with high efficiency. It seems with this reaction, currently with very high efficiency. So we try to start from the carbon monoxide and then study the carbon monoxide coupling reaction, and then to form the C2 plus product. We use the materials also has been synthesized in this most recent experiment. Is the work published in Nature Nano, the powerful nanosheet on the copper 111 surface. So we design a 1D surface. This is probably can be easily synthesized because at the initial stage of the paraffin growth, there must be the edges. The edges will form the 1D interface. So we use this interface, we demonstrate for the copper 111 surface, the carbon monoxide dimerization has a barrier 1.58 electron volt. By using the 1D interface here, we create an interface. The carbon monoxide dimerization, the barrier is only 0.42 electron volt. It's much lower than the pure for the pure carbon copper 111 surface. We also demonstrate that this can lead to the final product, the ethanol. CO2 product. Yeah, another example, we also look at the carbon dioxide reduction at the edge, not only at the interface, but the edge is also very interesting. We found that the silicon-doped graphene edges can be a metal-free catalyst for the reduction of carbon dioxide to the methanol and ethanol. Yeah, we hope the experiment can confirm our prediction in the future. Here in the future, this is, but probably it's difficult because it's metal-free catalyst without any transition metal. So I think I'm going to finish here with a summary and some notes on the topic of catalyst design for carbon dioxide reduction. So for the principle for the design, the catalyst, carbon dioxide reduction catalyst is based on the Sabatier principles. Sabatier principle, in practice, principle, the binding energy between the reactant and the catalyst should not be too strong and too weak. So we can design catalyst to tune the binding energy of the reaction intermediates. This where you can see from this picture, you can see here, now we use the catalyst, we can improve the reaction rate, change the reaction thermodynamics and kinetics. We can improve the reaction rate by the reduction of activation barrier for the rate determined step. But there's a challenge. Because according to the Sabatier principle, we need to optimize the binding energy. But based on the challenge, linear scaling relationship for the traditional transition metal catalyst, there's a linear scaling relationship because the binding energy for the linear scaling relationship, we can't optimize the binding energy of the reaction intermediate. So this is the challenge. That's why the challenge. For the widely studied copper catalyst, we have demonstrated both in experiment and in some theoretical work, we can modify the atomic coordination environment around the reaction environment around the catalytic active with copper atoms. We can use the different high index surface or stable index, and using the molecular adsorption, or we can use interface, and we can using alloy engineering. So we need to develop some strategy to design the carbon dioxide reduction catalyst. So firstly, we can discover some new catalytic materials. The well-studied catalyst is copper-based catalyst. So we can use a machine learning approach, high throughput computing. This is the computational approach. But we can also use a high throughput experiment to discover the new catalytic materials for the carbon dioxide reduction. For the catalytic design, we can also create an interface. Why? Because you can see here, for somewhere, we need to optimize the binding energy for the reactant here. But we can make the position a little bit higher. If the binding energy is too low, we can make it higher. We can create an interface. We can use a string, and we use some strategy to make the energy higher. And then thermodynamics and kinetics will be changed. This may become an effective catalyst. For binding energy too weak, we can introduce the defect and impurity and then enhance the binding energy. We can also tune the thermodynamics and kinetics and modulate the carbon dioxide reduction performance. So the catalytic design, we can try different approach. We can create in the interface, introduce the defect or impurity, and also change the coordinate number. We can use the high index surface, step surface. We can use the green boundary. Sometimes the defect, a green boundary is not a bad thing. Sometimes it can be good for the catalysis. We can use an edge. We can introduce the disorder. For example, when we introduce the order, the entropy will become higher. We can also introduce the asymmetry. When the asymmetry can promote the absorption of the reactant. We can also use a string, also in the electric field, also using the ferroelectric materials like we demonstrated here, because it has the polarization. We can use the charge transfer, make a charge transfer, modulate charge transfer, and using the molecular adsorption approach. But if using this approach, but the problem with some new challenges, will arise. For example, long-term stability. If you create a defect, the stability may become an issue. But also the larger scale synthesis may be also important to address. So finally, I would like to thank the financial support from Australian Research Council and also the computer time from the computation facility from our university and the Australian National Facility. For any question, please contact me by email. Any further question, you can ask questions. I'm happy to answer questions. Yeah, but it's better to be more theoretical, but because I'm from theoretical side. Thank you very much for your attention. Thank you.
Yeah, Professor Liu, thank you very much for your very insightful and very attractive talk on simulation and also on the carbon dioxide reduction. So I see several questions from the audience. The first one is about the artificial intelligence is becoming more popular in computational model such as the drug screen as well as catalysis. So is it common in predicting and design carbon dioxide reduction catalysts in this field?
Yeah, I think it's very important. Normally, we didn't use too much for the carbon dioxide, but we use for the other materials design for the material physics, because this will make your calculations very fast. Because you can write a Python script and interface with your program and make the calculations automatically. Even before, when you prepare your input file, when the job finished, you have to wait until tomorrow morning you submit your new job. But to make the calculation, artificial calculations, they can make all the calculations automatically, because the efficiency will be high. The calculation efficiency will be high. They will accelerate the material discovery, I think, yeah. It's very important, but also in drug discovery, carbon dioxide reduction, in particular for the high throughput computations is very important. Yeah, important. We have used a lot in my research actually. Yes, thanks. I'm not sure it's the answer you get it.
So I have the second question about the selectivity of carbon dioxide reduction. You know, there are many working on this field and the CO products, but you know, for the carbon 2, carbon 3 per hydrocarbon are more important. So from your computational modeling, so how to increase the selectivity on the carbon 2 and carbon 3 products?
Yeah. And this is a very challenging. I guess for both experiment as a radical rate, it's very long challenging question. But yeah, I think according to in my last slide, I showed something over there on the slides. The design catalyst try to create an interface, introduce something different using different strategy. For example, create an interface and also introduce, for example, a symmetry and polarization, and can probably and also experiment, also demonstrate the paper, the experiment I listed on the slide, published in Science lecture sister journal. You can see here the synthesized the C2 product, the mainly the using different approaches I mentioned in last slide to modify the atomic reaction environment of the copper atoms. Normally, we need to modify the copper atoms in reaction environment. Yeah, that's my answer. Yeah, it's a good question.
It's very helpful to rational design of emerging catalysts to get hydrocarbon products from carbon dioxide. Okay, so it's almost. I see the time is almost finished. So thank you, Professor Liu, as well as Professor Li, for your wonderful talk. So you know, green fields from materials is quite important to reuse or recant our results, and this is a very important topic for EcoMat journal. So welcome all the audience to submit your contribution to EcoMat. I'm sure it is a very good platform to broadcast your wonderful results. And also, finally, I'd like to thank Professor Lee and Professor Du again, because their work are very attractive and they can utilize the workings of carbon dioxide and also light to get workings of very important and sustainable chemicals. That's quite important. So I'd like to close the webinar, and please pay attention to the coming one. I'm sure EcoMat was a good field, and please join us. Thank you.
Okay.
Thank you.
It's very late in Queensland, so
Thank you.
bye bye. Good night. Good night.
Good night. Thank you.
Yeah, bye bye.
Bye bye.